All right, picture this. It is 3 a.m. Your pager is absolutely screaming, a critical dashboard is timing out, customers are hitting error screens, and you're bleary-eyed pulling up the logs. You stare at a SQL query that ran perfectly fine yesterday, but today? Today it's taking 30 seconds instead of its usual 300 milliseconds. Look, as someone who has spent way too many nights in the database trenches, I can tell you there is literally nothing quite as frustrating as an unpredictable performance cliff. For decades, we've just accepted this manual slog, right? Staring at explain plans, desperately adding index hints, and tweaking configuration knobs until the sun comes up. It's totally reliant on human intuition and a whole lot of trial and error. But what if it didn't have to be? What if your database could actually learn from its own execution history and autonomously predict the absolute most efficient execution path before a query even runs? AI for database query optimization. Welcome to the Explainer, folks. Today, our mission is to explore exactly how we're transforming that agonizing manual slog of database tuning by handing the reins over to machine learning. So, let's contrast the old world with the new. On one side, you've got legacy monolithic architectures, your traditional heuristic optimizers. These rely heavily on fixed rules, rigid assumptions, and frankly, completely arbitrary magic numbers. I mean, they assume columns are perfectly independent, which we all know is pretty much a fairy tale in any real-world production environment. On the flip side, we have futuristic learned query optimizers, systems with names like Lero, Balsa, and Neo. These act as tireless AI performance engineers. They're dynamic, they're autonomous, and instead of static rules, they use deep neural networks to learn the incredibly complex correlations hidden inside your specific data. They don't guess, they learn. And when we talk about a learned database system, we're really talking about a comprehensive AI brain. It's wild, but these systems can evaluate thousands of incoming SQL queries every single second. They are constantly monitoring real-time metrics like CPU, memory, latency, and throughput. They handle query analysis by estimating data volume using machine learning. They provide indexing recommendations for your entire workload. And they even use reinforcement learning to navigate the massive, complex search space of join orders to automatically optimize execution plans. Now, you might be wondering, how does it handle the sheer complexity of workload management? Because modern databases have hundreds of configuration knobs. Well, systems like AutoTune tackle this machine learning pipeline in 3 distinct stages. First up is workload characterization, which monitors runtime metrics and filters out the noise. Step 2 is knob identification, using algorithms to pinpoint the exact parameters that are actually going to move the needle on performance. And finally, the automatic tuner steps in. It applies deep reinforcement learning, which is essentially learning through trial and error to continuously optimize those hundreds of complex parameters without any human intervention. Okay, but we have to address the elephant in the room here. If these AI brains are so incredible, why hasn't every single engineering team on Earth replaced their traditional optimizers yet? Well, the answer is performance regression. See, a learned query optimizer might generate plans that are insanely fast 95% of the time. But what about that other 5%? Because of model underfitting or just unseen data, the AI might occasionally select an execution plan that is catastrophically slower than what your basic native optimizer would have chosen. And let's be real, in a critical production environment, you simply cannot deploy models that occasionally crash your systems just because they didn't recognize a new query pattern. There's a massive tension between aggressive speed and necessary stability. And that brings us to the architectural blueprint of a heavily vetted system called Eraser. This research is so solid it actually earned the prestigious ACM Artifacts Available badge. Eraser isn't some brand new optimizer trying to replace everything else. Instead, it operates as a safety net plugin that just sits right on top of any existing learned query optimizer. Think of it as a supervisor for your AI. It intercepts the candidate plans generated by the learned optimizer and evaluates how trustworthy the AI's cost prediction actually is. If the AI is highly confident, Eraser waves it through. But if the AI is clearly just guessing wildly, Eraser steps in and intervenes. So how does it do that? Eraser confidently runs a really clever 2-stage technical strategy to identify and discard unreliable candidate plans before they ever execute. Stage 1 is your core screened filter. If a candidate plan contains risky, unseen features, like, say, a table join the AI has literally never encountered before, it's immediately tossed out. Stage 2 takes whatever survived that first filter and evaluates it using segment models. These models cluster similar query plans together and associate those clusters with specific reliability intervals. If the predicted cost lands in a highly reliable interval, it executes. If that interval is wide and uncertain, the plan is rejected. And honestly, the benchmark metrics here speak for themselves. When running a complex IMDb workload, a pure learned query optimizer called Lero suffered from some pretty significant performance regressions. But the moment they deployed the eraser plugin on top of it, it eliminated 96% of those regressions. Literally, by just filtering out the candidate plans where the AI was basically guessing, Eraser effectively neutralized the single greatest risk of using machine learning at the database layer. Let's look at a few more real-world benchmark metrics comparing traditional Postgres, pure learned optimizers, and Eraser-enhanced optimizers across both stats and IMDb datasets. This really proves the magic of this architecture. Eraser-enhanced systems maintain the massive upside of machine learning, in some cases executing workloads nearly 2.7 times faster than native Postgres. But crucially, they achieve these aggressive performance gains without the risk of unpredictable outages. It effectively turns slow queries into optimized queries, while preserving that rock-solid stability that enterprise databases absolutely demand. Let's zoom out from the technical ML details for a second and look at the bigger picture. The business value of integrating AI tuning, when it's properly safeguarded by a framework like Eraser, is totally transformational. First off, it drastically reduces manual tuning effort, meaning your senior engineers can finally focus on architecture instead of just fighting fires at 3 a.m. Second, it systematically improves query speed. Third, it increases system scalability because this autonomous engineer literally scales with your data. Fourth, with those segment models and filters in place, it ensures high reliability. And lastly, it maximizes cost efficiency by extracting every single ounce of performance from the hardware you're already paying for. Which brings us to the ultimate question. Are you ready to let an autonomous AI performance engineer take the wheel of your database? The days of manual, heuristic-based tuning are definitely numbered, and they're being replaced by dynamic systems that finally offer both unprecedented speed and rock-solid safety. Thank you so much for joining me on this deep dive. If you found this explainer valuable, hit that like button, share it with your fellow engineers, and definitely subscribe to the channel for more. Until next time, keep your queries fast and your system stable.